My name is Jens Ahlich, and in this talk I'm going to present our analysis results on the Tetra encryption algorithm TEA3. This was a joint work with Armand Askeland, Supadeep Banik, Tim Baine, Anne Cantot, Patrick Felke, Gregor Leander, Willi Meyer, and Lucas Stanis. So, why is Tetra relevant, and what even is Tetra? In this collection, you can see some fields in which Tetra is used. We have, for example, airports, trains, the police, military, emergency services, and many more. And Tetra is about this, about digital radio. Tetra stands for terrestrial trunked radio. It is a two-way transceiver digital radio standard, which was created in the 1990s by the European Telecommunications Standards Institute, ETSI. What is special about Tetra is that it's not just used within Europe, but that it is deployed in more than 100 countries, and also that it is more widely used than its US equivalent. The Tetra encryption algorithms can be split into two sets. The first set consists of TEA1 through TEA4 and was created with the Tetra standard in the 1990s. They weren't published back then, but around 2023 they were reverse engineered by Midnight Blue and then revealed at Usenix 23. So TEA2 and TEA3 are for police, military, intelligence agencies, etc., where TEA3 is the export version of TEA2 for outside of Europe, and TEA1 and TEA4 are for commercial use. The second set, TEA5 through 7, were only created in recent years and were to replace the old ciphers for new security standards. In fact, they weren't published initially, only when ETSI changed their publication policy in 2024 did they actually publish the specification of TEA5, 6, and 7. Here, TEA5 and 6 are to replace TEA2 and 3, and TEA7 is to replace the commercial ciphers. While our main analysis is on TEA3, I will now first talk about the easy-to-break cases of the Tetra encryption algorithms, just to show why analyzing TEA3 is so relevant. Let's start with TEA4. This picture is from the specification. It's an 80-bit key stream cipher. As you can see, we have a 56-bit key register, and for the whole cipher to actually just be secure, we can't output every clock cycle, so only every 19th clock cycle we actually generate an output with a cipher. However, still we have a 80-bit key and just a 56-bit key register. So what they do is they compress the 80-bit key into the 56-bit key register by clocking it into, thereby reducing the effective key size to at most 56 bits. For TEA1, this is similar, just that the key register is only 32 bits. Additionally, for TEA4, when the ETSI published the specification of the cipher, because it wasn't included in what Midnight Blue revealed, while they included a table for the SBox lookup, as you can see, the SBox lookup is not complete because 4 values are missing. And if we assume bijectiveness for the TEA4 SBox, we can reconstruct them with those values. And as the ETSI published an updated version a couple of weeks ago, by now we know that those are the correct values. However, we will see later when analyzing TEA3 why we couldn't just assume that the SBox is bijective. Next, we come to TEA7. This is a cipher of the new cipher set. So now we have a 192-bit key and Ivy, but it's still a stream cipher. Nevertheless, it's now constructed with Rheindal in counter mode. They use Rheindal instead of AES, such that they can counter collision attacks on the initialization vector. This structure is actually identical for TEA 5 through 7, except for the input string where we have TEA 7 here. The only difference is you can see they don't use the key and ivy directly, but something they call mode key and mode ivy. And how they transform the key and ivy into mode key and mode ivy is actually different for the three ciphers. And for that, they use a combining function f, where they take 4 bits each of the cipher key and the initialization vector and transform them into the mode key and mode ivy. And this combining function f is different for the three ciphers. And in fact, for TEA7, they have a loss of entropy in this function, which reduces the effective key size. Here we can see the mapping of this function f. And if we now consider an input for the extended initialization vector to be 3, and we take a look at what all the possible output mode cipher keys are, then they are limited, and this reduces the effective key size of TEA7. So what is left? We took a look at TEA4, which is broken, TEA1 is similarly broken, TEA7 is broken, TEA5 is similar to TEA7, just without the weakness in the combining function, so it looks secure. TEA6 is similar to TEA7 without the weakness. That is now, actually, until the FSE published an updated version of the specification, there was a typo in the combining function of TEA6, which resulted in it not being a bijection, and thereby reducing the effective key size of TEA6. However, since the specification is much older than when they published it, it really just seems to be a typo. This leaves TEA2 and TEA3, and since TEA3 is the export version of TEA2, it looks more interesting. Now, finally, we come to the analysis of TEA3. Since TEA3 is one of the old ciphers, we again only have an 80-bit key, and the cipher is again a stream cipher built from a nonlinear feedback shift register. This time we actually have an 80-bit key register, so we don't need to compress the input key. First, we will only take a look at the key register. Here, we will look at a slightly transformed but equivalent representation where we take K0 as the output of the key register. However, first, we will only take a look at the S box. You can see that the whole feedback shift register is only nonlinear because we have the S box S. And as was already shown by Midnight Blue, this S box is in fact not bijective because there's one value which doesn't have a preimage and one value which has two preimages. What makes this unlikely to be coincidental is that the value that has two preimages is actually the value which is mapped to 0 by the S box. However, since we have the direct feedback of K0, we actually don't have a state collapse, so we didn't find an attack that uses this property of the S box. Now, if we assume S was linear, then we could in fact write the feedback shift register, we could represent it as a polynomial, which is factorizable. So
if it was linear, we wouldn't choose it like that. We would want an irreducible polynomial. And we thought like, okay, it's nonlinear, we can't apply the same technique, but maybe there is a way to decompose it as well. And since there was theory on bitwise nonlinear feedback shift registers, we extended it to bytewise nonlinear feedback shift registers. The theory you can find in the paper. Here I will give a graphical decomposition on the example of the TEA3 key register. So let's assume we have this key register, and now we take this state and add alpha 0 to alpha 4 on the first half, and alpha 0 to alpha 4 on the second half. This is a new state, so it's a difference, but we don't cover like differential cryptanalysis. It's just we consider two different states. And now K2 and K7 have the same difference, so the input difference to the S box is 0. So the output difference to the original state is alpha 0, and the feedback difference is alpha 0 as well. And if we clock further, this is still the case all the time. We still have this cyclic structure. So instead of having the difference in the original register, we can just write it as an additional cyclic feedback shift register. And now we can say, okay, K0 to K4 can be this difference. So we add K0 to K4 on the first half and on the second half, and put it in the cyclic feedback shift register, such that the upper part becomes 0. And next, we clock once, and can say, okay, we have this K5 plus K0. We can apply the same technique again. We add it to the cyclic feedback shift register. K0 becomes K5, and K10 plus K0 for the feedback becomes K10 plus K5. And we can repeat this every time we clock, such that the upper part of the nonlinear feedback shift register stays 0 all the time, such that we can take the input to the S box just from K8. We take the feedback directly from K6 plus K1, and we have to add it to the cyclic structure. And we no longer shift it into the new like upper half of the nonlinear feedback shift register, so we can just remove it. And now, as you can see, we have two feedback shift registers which are cascaded, the first one and the second one. And if we cascade those functions, we in fact get to the original function we had, so we were able to decompose it. And without going into too much detail, you can find the details in the paper. We were able to get some information about the cycle length of every period of the key register, because while the nonlinear feedback shift register part, the lower part, can have a cycle length of up to 2 to the 40, the linear part can add at most a factor of 10 to the overall cycle length of every period. All in all, our results are rather disappointing because neither the non-bijective S-box nor the decomposition of the key registers seem to have too large of a security impact. So additionally, we tried to do linear cryptanalysis and a time-memory trade-off on TEA3. For the linear cryptanalysis, we found that if it was clocked much less than 19 times, the cipher would break between, like 19 times between outputs. So it seems that they did linear cryptanalysis to choose those 19, but they didn't add much of a security margin. And the time memory trade-off shows that generic attacks are close to practical, but that's also the case for TEA2, because it's just that 80-bit key size is too small for now, like by now. Finally, we will take a look at the state register, which is initialized by the initialization vector, because if this part was linear, the whole cipher would break. So it's only nonlinear because we have these two functions, f31 and f32. So we tried to look into how were they constructed, and we found that, well, all those Boolean functions seem to have degree 3, and the function is still balanced. So in the paper, we tried to reconstruct the design criteria of how did they create those two functions that they are balanced and only depend on 2 input bits per those 2 input bytes each. As a conclusion, we have seen Tetris widely used, so it's very interesting to look into because the target surface is large. We still get intentionally weakened ciphers because TA7, they could have just chosen a cipher which has 56 bits instead of 192 and has a reduced effective key size. And we saw the decomposition of the TA3 key register. What else we have done, what you can see in the paper, is possible construction of those nonlinear balanced functions F31, F32. And we extended the theory behind the decomposition of bitwise nonlinear feedback shift registers to bytewise nonlinear feedback shift registers. This leaves us with the open question of whether there is a non-generic practical attack on TA3. Thanks.
Okay, thank you, Jens. Are there any questions to Jens?
Thank you. By your theoretical analysis, the cycle length of this key register is less than 2 to the 44. Did you make some, I mean, this is within computational range. Did you try out how long the cycle length for random keys actually is?
Yes, so we found all the possible cycle length for the small nonlinear feedback shift register. And for each cycle, you can find that there are only like 3 different factors which can increase the cycle length, which is either 10, 5, or 2. And we also tried to see what we can get and found that this is in fact the case, but we couldn't argue that only very specific ones are possible. We could reduce it to a small set, but we couldn't reduce it further to say the factor of 5 isn't possible or the factor of 2 isn't possible. Yeah.
So there's still time for questions. So any other questions?
Thank you very much for the talk. Do you think that with the decomposition of the function together with the decomposition of the first register in 2, it's possible to express some form from 1 cycle and 19 cycle ago among the output that you can get? I mean, is it possible to have this expression 19 cycles ago, or do you think it's exploding by using this decomposition of the function?
Do you mean in the Q register or in the full TA3?
Full TA3 in the output. Do you think it's imaginable to have the expression?
I mean, I would think that if there's actually a vector in the cipher, then this will play a part in it. But whether they accidentally included this decomposition or did it for some security we don't know about, or actually did it for a vector, I don't know. But we didn't find such a structure in the final output of TA3. So in the key register, you can get a lot of structure just from this decomposition. But since we have this nonlinear structure in the state register, which kind of works as a nonlinear filter function, we didn't observe anything we could reason about in the complete output.
Thanks.
Okay, so we are over time now a little bit. So thanks. Let's thank Jens again.